All right, so remember last time we talked about one-to-one. A function is one-to-one if it passes what, graphically? Horizontal line test, yeah. And what it means is essentially for every x there's one y, and for every y there's only one x. Functions that pass the horizontal line test and are one-to-one, we say are invertible, which means they have an inverse function that undoes their work. So I think we might not have finished up example 6 entirely. If you look at this graph right here, f of x was the blue one, and it asks us to find f of 2. So let's go ahead and do that. F of 2 would be 8 minus 2, which is 6. So on function f, there's a point called 2 comma 6. And then we know immediately that on f inverse, there is a point called 6 comma 2. So f takes a 2 and turns it into a 6. The inverse function then takes that 6 and puts it back in terms of a 2. What do we call those 2 points? They're not the same point. They are corresponding points. Good. We call these corresponding points. They're corresponding points. So once we found f inverse, we called it y inverse. Let me change that to f inverse. We can actually verify. Let's find f inverse of 6. That's how you'd have to show it, parentheses around it. If you plug in your 6, you get 6/4 plus 1/2. That's the same as 3/2 plus 1/2, which is 4/2 or 2. So we just kind of verified then that on f inverse, the point is 6 comma 2. All right, so as the bell was ringing, we sketched the graph of f inverse. It had an equation of 1/4 x plus 1/2. And I had y'all made, as the bell was ringing, to notice something about the slopes. The slope of the original function was 4, and on the inverse, the slope was 1/4, which is related to 4 how? Reciprocal, yeah. And they are reciprocals. Now, if you turn your head at a 45-degree angle, you can probably look at the pink graph and the blue graph and notice something about them. Okay, if you draw that line called y equals x, what can you tell me about the blue graph and the pink graph in relation to that line? Yes, they're reflections. Yeah, exactly. So f and f inverse are reflections across the line y equals x. And that's how you can get the graph of any inverse, by reflecting it, bless you, across the line y equals x. Y equals x is its own inverse, but it's also the identity function, which is why it becomes the magical mirror across which you can reflect any function to get the graph of its inverse. And it's not a coincidence that the slopes are inverses of each other, or reciprocals. They'll always be that. Okay, so here's example 7 then. It says, let g be the inverse of this function f. Find g of f, and f of g. Okay, so here's what I'm going to do first. I'm given the function f. I need to find its inverse. So I'm going to first call f y. It's just easier to work with y instead of f of x. Now the money step, remember, to find the inverse is the next one. And what do we do for the money step? Switch the x and y, right? So instead of y equals, we'll have x equals. And we have the cube root of y minus 1 minus 5. So switch x and y. And now we'll solve for y, which when we solve for y, again, what we're doing is we're doing the inverse operations in the reverse order. So it gives us kind of an algebraic way to find it. So if we add 5, we get x plus 5, and that equals negative 2, cube root of y minus 1. Now I have to get rid of the negative 2, so I'll divide both sides by negative 2, like that. And now I have to uncube both sides, so I'll cube it, and I'm left with y minus 1 equals x plus 5 over negative 2 quantity cubed. And the last thing I do is I add 1, and we get x plus 5 over negative 2 quantity cubed plus 1. And now that is the inverse, so we'll give it the name f inverse of x. And if you want to simplify it, you can. You can actually do this, x plus 5. You could cube the top and cube the bottom. Negative 2 cubed is negative 8 plus 1. So if you want to pull that out front now, you can call that negative 1/8 times x plus 5 cubed plus 1. And that puts it in standard transformation form. So it makes sense that the inverse of a function that takes the cube root of a number would have a function that cubes a number. Okay, so those are inverses of each other. So that's part A. It said to call it g of x. Okay, so we'll give it a new name. F inverse is a little bit, cumbersome, kind of a lot there. So very often we'll just give it another name, call it g. All right, so now it says to find g of f. What does that mean, g of f? Remember, that is composition, right? So g of f of x, that's the abbreviated way or the condensed way. That's the same as g of f of x. Okay, so here we go. We're going to then take the g function, which I just found. It was negative 1/8 times x plus 5 cubed. So x plus 5 cubed and then plus 1. And what am I going to plug in for x right here? Negative 2 cube root of x minus 1. Negative 2 cube root of x minus 1 minus 5. And guess what we get to do now? We'll simplify it, okay? So when we simplify it, we look inside the parentheses first, and it looks like there's some good things happening. Negative 5 plus 5. So then we're left with negative 2 times the cube root of x minus 1, quantity cubed plus 1. Well, now, inside the parentheses, I basically have two factors. I can cube each of them. So I have a negative 1/8 times. What's negative 2 cubed? Negative 8. Good. And then the next one, what's the cube root of x minus 1 cubed? X minus 1. And then we got the plus 1. Now we can combine like factors, or multiply our like factors together. Negative 1/8 times negative 8 gives us a positive 1, so we're left with x minus 1 times 1, which is itself, plus 1. And now what happens with the 1s? Sayonara, they cancel. And we're left with x. Is that surprising that we got x? It should not be, because how are g and f related? They're inverses of each other. So if you kind of look what we're doing here, we're starting with an input of x, right? We're starting with an x. We're applying the function f to it, which takes it, let's say, over here. And then we're going to apply the inverse to that, which undoes the work of f. It should take you right back where you started with what? X. We started with x, and we applied two inverses back to back. We ended up where we started with x. So it shouldn't be surprising. Now in part C, we're composing it the other way. F of g of x. So let's write it in the condensed version, f of g of x. And now the expanded version, f of g of x. So we're composing them the other way. And if you remember from Algebra 2, composition, or from the beginning of this section, composition in general is not commutative. $10 off and a 10% discount, it matters the order in which you take it. But what would you anticipate us getting here before we actually do the work? X again? Because we're starting with x. Now we're applying g, which takes us over here, and then applying the inverse, which should undo what we just did. It should take us right back where we started. So it should equal x. We're going to verify it. All right, so now we're starting with f, so that's negative 2 cube root of x minus 1, and then we have minus 5. And what are we going to plug into the space that I left for x? We're going to plug this dude right here. Let me actually copy him. And with Notability, we could just paste it in there. May have to shrink it down a little bit. There we go. Beautiful. Way to use technology. So that's the g function now sitting inside the f function where x used to be. Bless you. And now we'll simplify. We got negative 2 cube root of. Under the radical, we have a plus 1 and a minus 1. Those cancel. So we're left with negative 1/8 times x plus 5 quantity cubed minus 5 on the outside. Well, now since I have two factors, the negative 1/8 and the x plus 5 cubed, I could take the cube root of each of those separately. What is the cube root of negative 1/8? What times itself 3 times is negative 1/8? Negative 1/2, right? Negative 1/2. It's the cube root of negative 1 over the cube root of 8. And this one's a little bit easier. What's the cube root of x plus 5 cubed? X plus 5. Good. And then the minus 5 is still sitting out there. Now we can combine our factors that are like factors. Negative 2 times negative 1/2. Those divide out, leaving a 1. 1 times x plus 5 is just itself, x plus 5. Minus that 5. Holy moly, smokers. Guess what we're going to be left with? X. So there you go. F of g of x was equal to x, which was the same thing as g of f of x. Composition, as we saw in the beginning with the elephant blanket, it's not commutative in general, but here it appears to be that the order didn't matter of the composition, which means it is commutative. Doo-doo-doo. What relation did G and F have with each other again? They were inverses. Yeah. So when you compose two functions and then you do the same thing in the opposite order, if you get the exact same thing and if you get x, that's the same thing you should get both ways. If you compose two functions in either order and they give you x, that means that composition is commutative, which means G and F are going to be inverses. So here's a little theorem right here. It's an if and only if statement. It says if F and G are inverses, then F of G of x is going to equal G of F of x, and they're both going to equal x. But it also works this way. If I give you two functions and you compose them both ways and they get the same thing, they give you x, then that means F and G are inverses. It's an if and only if statement. So this gives you a way to check to see if two functions are inverses. So let's end with example 8. Let h be the inverse of g of x. What's the parent function for g of x? 1 over x. Very good. You would have to do long division if you wanted to put it in standard transformation form. We're not trying to graph this one, though. We're just trying to find the inverse function and then verify that it's the inverse by doing the composition. All right, so step 1, find the inverse. We're going to call g y, and we get 2x minus 1 over 4x plus 3. This makes a very good quiz question, by the way, and a very good test question. So now that I've called gy, what's the next step, the money step? Switch x and y. Good. So we get x equals 2y minus 1 all over 4y plus 3. Now algebraically, we just have to solve for y, but it's in two different places. So what would you do next if you had to solve for y? You could do the long division, but there's an easier way. Switch the y and the x? Very well, if you're going to interchange things, that whole thing and that whole thing can be switched. Their places can be interchanged. This is a proportion if you put it over 1. And anytime you have a proportion, you can always do what? Cross multiply. You can cross multiply. Yeah. So if you multiply down this diagonal, you'll get x times 4y plus 3 equals, if you multiply down the other diagonal, you get 2y minus 1 times 1, which is just 2y minus 1. So when in doubt, cross multiply. Now we're trying to get our y terms together. So what I have to do now is distribute. You're going to have to expand. So you get 4xy plus 3x equals 2y minus 1. Now it's a matter of collecting your y terms on the same side. I've got one on the left and one on the right. Let's collect them on the left. So 4xy stays there. 2y comes across now, and it's minus 2y. On the right-hand side, the 3x will go over and becomes negative, and the minus 1 stays there. Now, how are we going to get a single y factor on the left when those are not like terms? If it was just 4y minus 2y, we can combine them and call it 2y, but there's an x in the first term. So we can factor it out. Yeah, that's what you're going to have to do. You're going to have to factor out the y. So then you're left with 4x minus 2 equals negative 3x minus 1. And now you're almost there. Now you divide through by 4x minus 2. And you get y as negative 3x minus 1 all over 4x minus 2. And that could be the inverse. Now we're going to do one more thing to pretty it up. You have 2 terms in the numerator, 2 terms in the denominator. Of the 4 terms, 3 of them are negative. 3 negative terms and only 1 positive term. That's not very Rachel's challenge, is it? Having 3 negatives and 1 positive. We prefer to have more positives than negatives. So here's what you could do. Take your final answer and just multiply by negative 1 over negative 1. That's equivalent to 1, isn't it? Now when you distribute, you're going to change the sign. So you're going to get positive 3x plus 1, and then you're going to, in the bottom, have a positive 2 minus 4x. So not only did I distribute the negative in the bottom, but I commuted the terms. So now my 2, which is positive, is in the front, and now I have 3 positive terms, and then in the bottom right, trying to hide him, we got that negative term. That just looks a little bit better. And now I'm going to give that guy not the name y, but f inverse. So that is the equation that undoes the work of g of x. It told us to call it h of x. So, okay, I'll kind of do this. I'll just add h of x right there. It's still f inverse, but we can give it a different name. All right, so now that we found the inverse, we can check to see if we did it correctly by composing them. So let's go ahead and do now h of g of x. H of g of x. So now we're going to start with our h function, which is 3x plus 1. So I'm going to call that 3 parentheses plus 1. All over, the bottom is 2 minus 4x. That's 2 minus 4 parentheses. And what are we going to plug into the parentheses? G of x. That dude right there. This is going to be a lot of fun. Almost too much fun for a Monday. 2x minus 1 all over 4x plus 3. 2x minus 1 over 4x plus 3. So all we have to do now is simplify that. And when we do, we should end up with what as an answer? X, right? All right, fingers crossed. What did we just create, by the way? Mount Everest. Now it's back. Oh, Java. There's a new Java available. Thanks, Java. We just created a complex fraction, did we not? A fraction within a fraction. And we spent a lot of time this year going over how to eradicate complex fractions. State change flip doesn't work in this state. But guess what does? LCM over LCM. Very good. So you only have 2 miniature denominators, and they're both the same, 4x plus 3. So that's your least common multiple. 4x plus 3, 1 on the top, 4x plus 3, 1 on the bottom. And at this point, this should be pretty easy for you. When you distribute the 4x plus 3 to the first term, the 4x plus 3's divide out, and you're left with 3 times 2x minus 1. Plus, when you distribute to the 1 times anything is itself, you're just left with 4x plus 3. So that takes care of the complex fraction in the numerator. In the bottom, we'll do the same thing. We'll distribute, and we get 2 times 4x plus 3. When I distribute to the second one, I'm left with minus 4 times. The 4x plus 3's divide out, and you're left with 2x minus 1. So that accomplished our goal of getting rid of the complex fraction. Now we need to simplify all this. So the next step now is to expand everything out. A lot of algebra here, which is good. It's good for you, too. We get 6x minus 3. If you're yawning, you're not working hard enough, right? 8x plus 6 minus 8x plus 4. You should not be bored working these problems. All right, what happens in the numerator? Negative 3 plus 3? They're gone. In the denominator, 8x minus 8x? They're gone. And now if you combine the like terms that are left, you get 6x plus 4x, that's 10x. Over in the bottom, 6 plus 4 is 10. We're rounding third, heading home. In the 10th inning, base hit to left center. We're going to score. Walk-off single. Yes. After 5 hours and 14 minutes. X. We got X. We got X. That's what we expected to get, but now we know we did it correctly. Guess what we have to do now? That was h of g of x. Now we get to do g of h of x. Or I should say, you get to do it. I'm going to let you do that one by yourself. I'm going to do it up here by myself. You're going to do it right there by yourself. We're not going to talk until we're both done. This will be a quiz question this Thursday. On your mark is set, go.